Hello everyone, welcome to lecture 2 of week 10 of the course Power Network Analysis, in which we continue our discussion on the second last module, which is fault analysis. And in this discussion, we'll understand a very interesting theorem given by C.L. Fortescue 1918, where he came up with this indigenous concept, again named after himself, that for analysis of faults in three-phase networks, specifically for unbalanced faults or asymmetric faults, the associated discussion that we have had yesterday, not yesterday, in the previous lecture, which was on balanced fault analysis, the same analysis, if it were to be applied for unbalanced or asymmetric faults, then the associated equations that one has to deal with become highly complex, they become coupled, and eventually they become unsolvable. I mean, there is a way to solve them, but then the associated burden would be very high. So C.L. Fortescue came up with this concept, which he named, again, was well known after his own name, known as Fortescue's theorem, in which in 1918 C.L. Fortescue stated that any n-phase network or any n-phase system, specifically when I say n-phase system, I am pertaining to n phasors where n can be more than equal to 2. Obviously, n is belonging to set of integers, positive integers to be precise. For n equal to 2, 3, 4, 5, for three-phase system, n is equal to 3. He stated that all these n-phase systems where we deal with n voltage phasors or n current phasors, these voltages and currents could refer to phases or line-to-line quantities. All these n phasors, they can be represented as n systems of balanced phasors. That means each phasor in this n-phase system can be represented as n individual components, and each of these components would pertain to a system of balanced components. So with this, what happens? C.L. Fortescue came up with this transformation, and in this transformed way of analyzing the unbalanced or asymmetric faults becomes easier because the associated equations become decoupled, they are independent. And these systems of balanced phasors are essentially what are known as sequence components or symmetric components. So let's see in details what is it all about. So asymmetric faults or unbalanced faults are all faults in except the three-phase fault. In three-phase system, for n is equal to three-phase system, the possibilities of unbalanced faults or power network, n-phase power network, the unbalanced faults, they can pertain to single line to ground fault, line to line fault, or double line to ground fault. So just to give you an idea, what do I mean by single line to ground fault? If I have a transmission line with phases phase A, phase B, and phase C, and I have to understand what is a single line to ground fault, then probably in one such case, if phase C gets shorted to the ground through some fault impedance ZF, then I would call this particular single line to ground fault as phase C to ground fault, G referring to ground. There could be other two possibilities of, instead of phase C getting shorted, phase B might get shorted to the ground through a fault impedance, or the other alternative or last possibility is, instead of phase B, phase A itself might get grounded while the other two phases remain healthy and carry the normal load current. So in single line to ground fault, we can have three possibilities: phase A, B, C respective to the grounds. For line to line, ground doesn't come into picture. Any two phases are getting shorted through each other through some fault dependence. And lastly, the third category is double line to ground fault, which involves two phases and the ground, which are shorted through some fault impedance ZF. So basically, we would have 9 such asymmetric or unbalanced faults. And why are they called asymmetric? They are called asymmetric because the corresponding post-fault voltages and currents that we would observe, we have still not figured out how they have to be obtained. They would inherently remain balanced no matter whether the system in the previous condition was balanced or not. Now, what do I mean by balanced or unbalanced? We have briefly talked about it in the basic circuit principles module, in which we say that balanced phase system, specifically for three-phase system, if I'm talking about a balanced three-phase system, then in that balanced three-phase system, the voltage phasors for each of the phases, they have equal magnitudes and they are 120 degrees spaced apart, and the corresponding orientation in which these three phasors of voltages can exist, we associate them inherently to be the positive sequence voltage, because coincidentally our three-phase synchronous generators inherently generate this three-phase positive sequence voltage. So positive sequence voltage is one such notion of balanced system. By balanced, I mean here specifically that the corresponding phasors that existed in the network before the fault occurred, they correspondingly pertain to positive sequence voltages or currents consecutively. Positive sequence voltage or current in which all the three phases of a particular voltage or all three phase voltages have equal magnitude and they are 120 degrees spaced apart with positive sequence orientation. There can also be another balanced phase system which could be called as a negative phase system, in which the magnitudes of phases are same, the phase angles are 120 degree apart, but they are in a reverse orientation compared to positive sequence orientation. And lastly, the third balanced system which can exist in three-phase systems is the zero sequence component, which coincidentally can exist as a common system for any n-phase system where n could be 2, 4, 5, 6 and whatnot. So the unbalanced faults or asymmetric faults, they inherently produce a post-fault unbalance no matter whether the pre-fault condition was balanced or not. And the problem with unbalanced analysis, as I mentioned in the beginning of our discussion, is that because of coupling which comes in because of the associated equations, solving those equations becomes difficult, and hence sequence components or symmetric components play a very important role. For balanced systems or for balanced faults, we have understood the application of Thevenin's theorem, and since everything remained balanced both in pre-fault and post-fault condition for balanced faults, so use of single line per unit diagram was sufficient enough to apply Thevenin's theorem. The same Thevenin's theorem, although with little bit of extension, may be used for symmetric, unsymmetric or unbalanced faults, but then the bridge to applying Thevenin's theorem has to come with the application of the symmetric components or sequence components for unbalanced faults. Phase-based analysis for Thevenin's theorem application for unbalanced faults won't be feasible, won't be realizable because of the coupling effect. So as I mentioned, Fortescue's theorem, it essentially results in resolving a set of unbalanced three-phase system. This three-phase system could pertain to voltage phasors or current phasors. Any unbalanced voltage or current phase system can be resolved into three distinct systems, where each of these systems would inherently remain balanced no matter what is the level of unbalance present in the actual network. So in three-phase network, those components we would call them as positive, negative and zero. We have briefly discussed about this in the basic circuit principles also, and there is a dedicated proof which exists as per Fortescue's work, which states that this n-phase system can be always resolved into n systems of balanced systems, and the beauty of such a transformation is that these systems would all remain decoupled. That means a positive sequence element or a component will never ever appear in a negative sequence circuit. Zero sequence component or circuit element would never ever appear in a positive sequence circuit, and that's how these three components or systems are perfectly decoupled or independent of each other, which aids in analyzing our unbalanced or asymmetric faults. So decoupled, as I mean that the system is, each system is independent of each other. Balanced phases, as I mentioned, each of the phases in a n-phasor system, they are to be of equal length with equal angles among each other. These components would be called as symmetric or sequence components. In physicality or real world, these components or systems don't exist. They are just a mathematical premise of creating a bridge between the actual unbalanced quantities and the corresponding fault analysis that we would do. Although there are ways of measuring this, but if one were to specifically pinpoint out, okay, please identify me a element where a negative sequence current flows, it's difficult to pinpoint it out. Although negative sequence current flows in its own way, there are ways of measuring it out, but in reality these components don't exist in the actual network. That's what I mean to say. For example, if someone asks me or asks you to identify me the part of the synchronous generator where negative sequence currents can exist, they can exist in the network as it is, but it is very difficult to pinpoint or identify that, okay, in this particular winding negative sequence current is flowing. So that's what I mean by their fictitiousness and having no physical presence in reality. These components can, as I said, could be in terms of currents and voltages, and on similar lines, sequence impedances can also be defined, although the definition of impedances is a little bit different from sequence voltages and currents. So we'll understand first what do we mean by these sequence voltages as defined by Fortescue's theorem, and then we will try to see what do I mean by the sequence impedances and what are the difference. So for three-phase system, three-phase power network, Fortescue's theorem says that again n is equal to 3 system of independent balanced systems can exist, and those systems are nothing but positive sequence, negative sequence and zero sequence in terms of voltages. These phasors can also be drawn in terms of corresponding currents. These currents could refer to line currents, phase currents. In terms of voltages, they could also pertain to phase voltages or line to line voltages. Positive sequence voltage is the inherent form of operation or natural form of operation of a balanced power network, because as I mentioned, synchronous generators inherently produce these voltages as per their design. Negative sequence and zero sequence voltages, they may turn up mathematically, or negative sequence current or zero sequence currents may turn up mathematically under certain unbalanced conditions. As long as the system is balanced, we would have only the presence of positive sequence voltage. For balanced operation of this three-phase network, these components will never ever exist. Why? We will see that as we progress in these slides or in the next lecture slides. That is one aspect. The other aspect is that Fortescue theorem, it only says that for n is equal to 3, there can be 3 distinct components, positive, negative and 0. Fortescue's theorem also added one more definition, that suppose if I have, don't confuse these with VC, VA and VB. I'm just going to write a particular equation. Suppose I have a phase A voltage pertaining to the output of a three-phase synchronous generator, let's say the terminal voltage, which is, let's say, VA. This is a common bus, but these buses might be different. I have VA, VB, VC as the 3 terminal voltages, phase voltages of the three-phase synchronous generator, and I want to understand how these 3-phase voltages VA, VB, VC, what have they to do with the corresponding sequence components, positive, negative and zero sequence component. So Fortescue stated that if I have to denote phase A voltage in terms of the corresponding sequence components, which for phase A correspond to VA1, which is the positive sequence phase A voltage, VA2, which is the negative sequence phase A voltage, and VA0, which is the zero sequence phase A voltage, then VA is nothing but VA1 plus VA2 plus VA0. This is again as per Fortescue's theorem, and a well-dedicated proof for this sort of analogy already exists in the literature. Similarly, for phase B voltage, if I have to express it in terms of the respective sequence components, which are VB1, let me write those as VB1. So actually this cross here, they pertain to VB1, VB2 and VB0. So phase V voltage is VB1 plus VB2 plus VB0, and similarly phase C voltage would be VC1 plus VC2 plus VC0, where VC1 is the phasor defined over here, VC2 is the phasor defined over here, and here we have VC0. Now this is again as per Fortescue's theorem, and the beauty of this correlationship is that at the outset it might appear that on the right hand side of these three equations there are 9 variables which need to be identified, 3 for every such phase. But in practice, as per again Fortescue's theorem, in reality 9 variables at the outset that need to be identified for identifying the sequence components. But as per Fortescue's theorem, if we identify only 3 variables, then the remaining 6 variables remain known. So 3 variables in reality. If we know these 3 variables, then the other 6 terms or all 9 terms in the RHS component would become known. What would be those three variables? Those 3 variables correspond to sequence component of any one phase. So let's say if I choose phase A as my reference phasor or choice or suitable phase reference, and if I identify the positive sequence voltage of phase A, negative sequence voltage of phase A, and zero sequence voltage of phase A, I can associatedly also find VB1. What would be VB1? VB1, as per the positive sequence diagram, VB1 is lagging VA1 by 120 degrees. So VB1 would be VA1 at an angle minus 120 degrees, which is what is precisely defined over here. Similarly, if I have to find negative sequence voltage of phase C, then as per the negative sequence diagram, VC2 is lagging VA2 by 120 degrees. So VC2 is VA2 at an angle minus 120 degrees. And as per the zero sequence diagram, where phase voltages are again equal and the phase angle is 0 degrees imperfect, so VB0 is same as VA0, which is same as VC0. So in a way, if I know what are these 3 sequence components, I can identify remaining six components. So that's where the uniqueness comes in, and in practice this sort of a equation becomes solvable because I have 3 variables in reality which pertain to any phase sequence component, and I also have 3 equations from which these 3 variables can be solved. It's a win-win situation, n equations to be solved for n unknowns, and that's how the Fortescue's theorem can be physically realized. So with this, let us go a little deep into what are the mathematics involved. I hope this understanding or this discussion is clearer to all the viewers. So to sort of simplify our discussion, we will define a complex operator A, which is a phasor of magnitude 1 and phase angle of 120 degrees. And as per the diagram of positive sequence voltage, if I have to express VC1, which is VA1 at an angle 120 degrees, and having defined small a, please don't confuse this A with the phase A reference. This is a different operator, which is being defined as A at an angle 120 degrees. Then VC1 is nothing but small a VA1. Similarly, VB1 is actually leading, in a way, if I were to say, it is leading VA1 by 240 degrees, where A square would be 1 at an angle 240 degrees, then VB1 would be A square VA1. You could also say that, sir, A square is also equal to A conjugate. Yes, A square will also be equal to A conjugate, because A conjugate is 1 at an angle minus 120 degrees, which is same as 1 at an angle 240 degrees. So A, the complex operator that we define here, becomes very critical, and this value of A satisfies these 2 equations. Please verify. It can be easily seen why does A verify this. So if A is 1 at an angle 120 degrees, A square, as I mentioned, is 1 at an angle 240 degrees. A cube would be 1 at an angle 360 degrees. 360 degrees is equivalent to 0 degrees, which is same as 1, and that's why A cube is equal to 1. And A square plus A plus 1 is equal to 0. That is well observable through the respective positive sequence or negative sequence diagrams. If I associate this as 1 at an angle 0, then on this side I have A, and this side I have A square. The sum of these three phasors, the resultant component is always going to be 0, and that's why this equation is valid. Using this A operator, I can define phase A voltages in terms of the corresponding sequence components with respect to phase A again. VA0, VA1 are sequence components of phase A, and I can define this capital A matrix, which is in terms of 1 and the small a operator. The inverse of this A is also a beautiful similar matrix compared to A matrix, and this equation tells us that I can find the phase component, symmetric components using A inverse of phase A voltages. Similar relationships also exist for the currents. For balanced systems, where by balanced I mean that inherently I am working with positive sequence voltage. For balanced systems, which in this case particularly refers to positive sequence operation, because that's the inherent nature of operation of power network. As you can see, IA, IB and IC, if they are all positively sequenced arranged, negative and zero sequence currents won't exist. So these three phasors, they would eventually add up to 0, and that's the reason why zero sequence currents can never exist in balanced positive sequence operation networks. For unbalanced systems, when they are ungrounded, zero sequence current will still be 0. The answer lies in the notion of the part being ungrounded. If I have a star grounded connection and this neutral point, well, let's say if this is a load where the three-phase load is carrying currents IA, IB and IC, and this load here is star connected, but it is not grounded. It is, the neutral point is still open. If I apply KCL at this neutral point, what I would observe, I would still see that the phase currents IA plus IB plus IC, their sum will always be 0 because of the KCL at the neutral point. So no matter whether phase A, phase B, phase C currents are balanced or unbalanced, for ungrounded systems where the neutral points are not connected to the ground, the zero sequence currents, which are again average of the individual phase currents, they would again be 0 because of KCL at the neutral point. For unbalanced grounded systems, the zero sequence current need not be 0, because if it is now grounded, there can also exist a neutral current which would be 3 times of the zero sequence current. In terms of power, the three-phase powers, they can be expressed in terms of this matrix product, which again pertains to 3 times of individual sequence-based powers. This is basically zero sequence power, this is positive sequence power, and this is negative sequence power. If the components themselves don't exist, these power definitions also, notions also are fictitious quantities, just mathematical definitions. Coming to impedances, the notion is a bit different. The notion here is that for a given positive sequence circuit, if there exists a positive sequence voltage which is leading to some positive sequence current, then the corresponding impedance offered to flow of this positive sequence current in the positive sequence circuit would be called as positive sequence impedance. The way sequence components are extracted from three-phase voltages or currents, the same way of extraction won't hold true for impedances. It is just that the impedance offered to positive sequence current would be called as positive sequence impedance. Negative sequence current, which the impedance it's experiencing would be called as negative sequence impedance, and similarly zero sequence impedances. These have no direct implication, or I would say these don't, they do depend on the phase impedances, but their relationship in terms of sequence voltages or currents, the same notion don't hold true for impedances. So let's see what those impedances look like. So what I have considered here is a very generic three-phase star connected, star grounded in fact, star grounded load, and this load is balanced. That means each phase is having the same impedance observed across it, and these three this three phase balanced load might also be having mutual coupling along with it, and the neutral point, which is this point over here, it is grounded in terms of a neutral impedance Zn. So if I have to understand what are the corresponding positive sequence impedance, negative sequence and zero sequence impedance of this three phase balanced load, which is having self impedance Zs in per phase, Zm as the mutual impedance and Zn as the neutral impedance, how do I proceed? It's always good to start with the basics in the terms that to analyze this three phase balance load, what we would do, we would apply KVL, KCL and get the corresponding equations for given knowns, unknowns. We'll solve the corresponding equations and then understand how this load actually behaves. So let's do a similar exercise here. If I apply KVL for phase A voltage, which is, let's say, the circuit over here. If I apply phase KVL between phase A and the ground point, then I would eventually traverse the path along phase A, come to the neutral point and reach the corresponding ground point. So if I write the corresponding equations, as I'm starting with phase A terminal, so I'll have VA minus IA into ZS, which is the voltage drop across this self impedance. Remember, these impedances are also mutually coupled. The dot polarities have not been marked, but assuming that the dot polarities are all additive, then I would also have voltage drop because of other phase currents, which would be IB Zm and similarly IC Zm. That leads me to this neutral point. After the neutral point, I have Zn impedance, so I have minus IN Zn, and then eventually I reach the ground point of the neutral point, which is having a potential 0. Now this neutral current, what is its expression? By KCL at neutral point, neutral current is nothing but IA plus IB plus IC. So instead of IN, I can put these three currents over here. Similar equations can also be written for phase B and phase C. I'll have the three-phase system, which is essentially what is shown over here or marked over here. Since neutral current IN is IA plus IB plus IC, so every correct 3 cross 3 matrix of the Z matrix consists of the Zn component. And I know for sure that this 3 cross 1 matrix, VABC 3 cross 1, is nothing but capital A matrix, assuming phase A as reference for sequence components, which is VA0, VA1, VA2. And similarly, phase A IABC currents are capital A, assuming phase A as reference for sequence components, IA0, IA1 and IA2. So I can eventually convert these phase quantities into corresponding sequence components and do some mathematical observation, which is where I get this as my corresponding matrix. The value of capital A has already been discussed or given in the previous few lectures. And now if I evaluate this expression, I would get this 3 cross 3 matrix, and I would call the first element here to be the zero sequence impedance, the second component to be the positive sequence impedance, and the third component, which is coincidentally same as the positive sequence impedance, we'll call them as negative sequence impedance. How do I arrive at it? The arrival of this conclusion comes from the definition of VA012 and IA012. If I expand VA012, it is VA0, VA1 and VA2. And similarly of IA02, I have IA0, IA1 and IA2. And if I go back and look at my definition of impedances, as per this statement, the impedance offered to flow of zero sequence current because of zero sequence voltage would be called as the zero sequence impedance. And that's the reason why the first term is zero sequence impedance. Similarly, the second term, which is relating VA1 with IA1, is positive sequence impedance. And lastly, the third term is correlating VA2 and IA2. So respective impedances lead to corresponding drops in their respective components only. They don't mingle or cross each other. I intently chose this three-phase balanced load having mutual impedances where the resulting equations, if I see in terms of impedances, it was a full 3x3 matrix. The moment I convert it into sequence impedance part, I only see a 3x3 diagonal matrix. The other off-diagonal terms are all 0, relating that positive sequence has nothing to do with zero sequence. Negative sequence has nothing to do with positive sequence, and that's where the decoupled part comes in. For balanced load, the three sequence networks, they appear to be all independent as per this 3x3 matrix. In similar lines, we can have definitions of impedances for transmission lines and transformers, static devices. The orientation or notion of positive and negative sequence doesn't matter because the geometry doesn't change irrespective of the sequences, and hence for transmission lines, positive and negative sequence impedances are same as the actual line impedance, which we have discussed and evaluated in module number 4, which was, I think, transmission line parameter evaluation. Same is also true for transformers, except that the corresponding, instead of line impedance, here the transformer's leakage impedance comes into picture, which is same as the positive and negative sequence impedance of transformer. Zero sequence impedance, it significantly depends on the where the ground is connected or the shielding wires are present. So zero sequence impedance of lines is usually 3 to 5 times of the corresponding positive sequence or negative sequence line impedance. For transformers, it all depends on what the configuration of transformer is, whether it is star connected or star ungrounded or delta. The configuration of transformer may or may not allow the flow of zero sequence currents, and it is all because of the fact that in case current has to flow or appear in the primary winding, it gets linked because of MMF balance, because of flow in secondary winding. This aspect we have extensively discussed when we were discussing about transformers, that how the primary gets to know because of change in secondary current. Why does primary also respond? It is all because of the MMF balancing aspect, the physics which goes behind operation of transformers. So in case of transformers with different configurations, if secondary circuit has to carry current, primary might carry current depending on the configuration, thanks to the MMF balancing aspect. If zero sequence current flows, then the zero sequence impedance would be same as the leakage impedance of the transformer. Also, in terms of transformers for dissimilar configurations, we have seen this 30-degree phase shift between star and delta transformers, thanks to the way they are connected. So in order to understand the impedance, zero sequence impedance for transformers, we would actually make use of this MMF balancing act and understand whether zero sequence impedance can exist or be present for three-phase transformers. So for three-phase networks or three-phase transformers, we have 4 possible configurations of transformers: star grounded, star grounded. If zero sequence current can flow, which is going to be the current IN, which is going to be 3 times of the zero sequence current on the primary side, and here we might have IN2, which is not IN2, let me say INHV and INLV, which is 3 times of zero sequence current on the LV side here and the HV side here. If this current can exist because of the neutral current being available, then here also the zero sequence current can flow, because here also we have a grounding connection, and that's the reason why this circuit here pertains to the associated zero sequence representation of a star grounded transformer. If zero sequence current can flow on the HV side, a similar current can also flow on the LV side. There is a possibility of zero sequence current to flow through the zero sequence impedance. In case the neutral is ungrounded, then the current might exist over here, but if over here there is no path for the neutral current to flow to the ground, because zero sequence current has to flow to the ground, then here INLV is exactly 0, and if secondary current is 0, by MMF balancing act, this current, although there is a path, this would also be 0, and that is what indicates this break between A and A dash. A is, let's say, the primary side, which could be the HV side or LV side, and A dash here refers to the secondary terminal. The primary and secondary terminals in zero sequence circuit for three-phase transformer is unconnected for star grounded and star ungrounded, because here zero sequence current can't exit out of the terminals. For star grounded and delta configuration, the zero sequence current can exist because there is a path for the current to flow here. But on the terminal or the secondary side, zero sequence current can't escape out of the terminals. It can flow, but essentially the zero sequence current flows as a circulating current. It doesn't escape out on the terminals. And that's the reason why we have this sort of a configuration for star grounded delta connection, because on the primary or HV side, zero sequence current can exist which can go through the ground, which is indicating this component, but it cannot exceed out on the terminal which is on the secondary side because of delta connection. And lastly, for star ungrounded and delta, here current cannot exist, so the series break indicates that break, whereas on the delta side there is no escape possible. Although this part is grounded, the corresponding break here indicates that delta connection. For delta-delta transformer, none of the terminals can have the presence of zero sequence currents because there is no path for the zero sequence current to escape out. So in a way, the zero sequence currents won't exist on the primary or secondary side for a star delta-delta transformer. In case the neutral grounded is connected, which is indicative of this neutral impedance, then as we have seen in terms of three-phase balanced load, which was this term over here, 3 times of neutral impedance was appearing as the zero sequence impedance. Same is also applicable for transformers. If the transformer is grounded through some impedance Zn, then it will have 3 times of its component present over here. For synchronous machines, we will discuss about the corresponding sequence components in the next lecture, where since we're talking about fault analysis, so synchronous machine have to be represented by the internal EMF and direct axis subtractant direct axis reactance. So we will see with XD double dash how the sequence components or impedances would look like. So that's what we would continue in our next part of unbalanced fault analysis. Thank you so much.